Hey everybody, it's Mr. Stoltenberg again. Starting our next video, it's going to be an introduction to acids and bases. We're going to look at the chemistry of them and kind of the chemistry that's behind where acids and bases come from. Um, Probably won't get to calculations in this video, but that's something we'll eventually end up doing is pH and pOH calculations, which will be super tons of fun. So, all right. You've seen this before. This is kind of just a general review of the general characteristics of acids and bases. We'll go through some of this stuff in more detail. But if you know this much information about acids and bases, you're off to a good start. It's enough to answer a lot of questions. All right, well, let's go. Okay, when talking about textbook definitions for acids and bases, there's actually two accepted um, versions for each. There's the Arrhenius definition and there's the Bronsted-Lowry definition. They're kind of saying the same thing, but there's some slight differences between the two definitions that make it a little slightly different, so why the need for the distinction? So let's look at the definitions for acids. Arrhenius acid is any substance that when dissolved in water produces more of the hydronium ion. Hydronium ion, we'll talk more about that in a second, H3O plus ion. So it's a substance that dissolved in water, the concentration of hydronium ion will increase. Okay, well that's all fine and good, but not every acid involves the solvent being water, so it kind of somewhat limited just to acids where the solvent's water. Bronsted-Lowry definition is a little more broad, and it's pretty simple. They call the acid is known as the proton donor. And when I say proton donor, what I'm actually talking about is I'm talking about a hydrogen ion, an H plus ion. It has a hydrogen that it gives up once dissolved, and that's what makes it a proton donor. So that's the Bronsted-Lowry definition. A little more broad. It doesn't limit you to the solvent of water. Okay, then this kind of similar with definitions with bases, except we're not talking about H plus. We're talking about hydroxide. So an Arrhenius base is any substance that, when dissolved in water, produces more of the hydroxide ion. So it increases the concentration of hydroxide. However, not all bases have hydroxide in them. NH3 is a good example. So under this definition, NH3 wouldn't classify as a base, but it is a base. So we need a little bit broader definition. So again, Bronsted-Lowry definition is a little bit broader and kind of more encompassing. And again, it's very similar to the acid, but the opposite. So where the acid is the proton donor, a base is the proton acceptor. So a compound that's capable of receiving that H plus ion. All right, so those are your textbook definitions. If you know those word for word, you'll be good. The only issue I've seen in the past is people flip them, and that's really the only way to mess these up is to flip them. So just don't flip them. All right, so what is the hydronium ion? Where does it come from? Well, this is a generic expression that shows you what the hydronium ion is. Lone H plus ions don't exist in water solutions by themselves. If a compound releases a hydrogen when dissolved in water, that hydrogen isn't just floating around by itself. What it actually does is it attaches itself to the water. So this is your acid right here. This is the hydrogen that the acid is going to lose. Well, instead of being free floating H plus floating around, it will actually attach itself to this oxygen in water and create an H3O plus hydronium ion. It's a water molecule with an extra hydrogen attached to it. Now here's the kind of tricky thing. I don't. It's 100% acceptable to say hydronium ion. It's also 100% acceptable to say H plus or the hydrogen ion. In acid-base chemistry, it's basically talking about the same thing. So you'll actually see both. You'll hear me say H plus sometimes, and you'll hear me say hydronium sometimes. You just have to understand it's talking about the same thing. Because technically H plus doesn't exist by itself. It's actually hydronium ion. But, writing H plus is shorter than writing H3O plus. And you know how scientists like to abbreviate everything. So one is used just as much as the other, and they're both considered acceptable. All right, so let's look at a couple reactions here and see if we can't see these, how an acid and a base are acting. So here, again, Bronsted-Lowry definition: the acid is the proton donor, the base is the proton acceptor or the proton remover. So here we have nitric acid, HNO3, and we have ammonia. Sorry, not ammonium. Ammonium's right here. The acid is going to give its hydrogen to the NH3. The NH3 is going to accept it, and our products will be ammonium ion and a nitrate ion. This is your proton acceptor, so this is your base, this is your proton donor, this is your acid. We know from previous units, acid nomenclature, that we were always looking for that hydrogen up front. That's what made it an acid. Well, now you're seeing why it's actually considered an acid, because it's going to be giving that hydrogen up. That's what technically makes it an acid. So there you go. But again, for us, if you're trying to identify the acid, just look for that hydrogen up front. So here it is in just a different format. So nitric acid donating the hydrogen, ammonia accepting it. All right, here's another example, but this time we're reacting the acid with water. So HNO3 is our acid source. Water is our going to act as our base because it's accepting the hydrogen. So the nitric acid gives up the hydrogen, the water accepts it. So in this case, nitric acid is clearly the acid, but water is acting as a base because it's accepting that hydrogen. Interesting aspect of water is that not only can it accept hydrogens like it is here and act like a base, but it also can donate. So you mix a strong base with water, and now water, instead of being the proton acceptor, water is the proton donor. NH3 is going to take a hydrogen from that water molecule and give us NH4 and a hydroxide ion as our products. Here, water is acting as the proton source, the proton donor, so it's acting as an acid. And this is one of the cool things about water, is that it can act as both an acid and a base. That property, that ability is known as amphoteric. It's not something you absolutely need to know, but it's a word that might get mentioned every now and again. Just kind of a cool aspect of water. So let's look at these examples and see if we can identify the acids and the bases in each one. Relatively simple process here. Just look for the transfer of that hydrogen and look to who's accepting it. So here we have HCl and aluminum hydroxide. Well, HCl, hydrogen up front. Boom. It's going to accept that hydrogen, or it's going to donate that hydrogen here. Hydroxide is another big clue. We know how to recognize acids by the hydrogen up front. Well, here's one of the easiest ways to recognize a base. Hydroxide. You see hydroxide in a compound, and I promise you it's a base. So aluminum hydroxide's your base. Acid, base. All right. barium hydroxide and acetic acid, acid, base. Hydrogen up front makes it your acid, hydroxide makes it your base. Easy to identify. Again, KOH, that's your base. Hydroxide makes it your base. Hydrogen up front makes it your acid, sulfuric acid right here. Okay, well, what if your base doesn't have hydroxide in it, or if you're using water? Well, you just have to look at how the transfer of hydrogen is occurring, and that'll tell you whether your water is acting as an acid or a base. So here again, it's reacting with NH3. We look at our products. We see water has lost a hydrogen, NH3 has gained a hydrogen. So in this case, water is acting as the proton donor, so water is the acid, NH3 would be the base. Pretty simple. We'll talk about these kind of reactions again a little later. These are known as acid-base reactions or neutralization reactions. We'll spend some more time talking about those in a later video. All right, let's talk about the pH scale. pH scale, this is a measure of how acidic something is, basically. You probably have heard this term before in reference to maybe soil if you're in an agriculture class, or pH of water is something that people monitor in swimming pools and other wildlife resources where the pH of water is if it changes, it can have significant impact. What it's actually measuring is the concentration of hydrogen ions. pH scale is essentially telling you how concentrated the H plus ions are in that solution. It's simply a measure of concentration. And if you remember from last unit, measures of concentration involves molarity, and guess what? Going to pop up again. That's right, we're going to be talking about molarity later on in this unit. A little interesting side note here, pH. The guy who created the scale, or this might be an urban legend or not, but this is how I know the story. The guy who created the pH scale died kind of unexpectedly. Well, in his notes, he never indicated anywhere in there what the P stands for. So to this point, what the P actually stands for is kind of a mystery. It's just why use the P or what it means. It's kind of a mystery because the guy who originally created the scale never indicated it in his notes and died before anybody could ask him. A lot of people think of it, or this is one of the ways I like to think of it. I think of it as the power of hydrogen. How much hydrogen, how strong the hydrogen is in that solution. It's kind of a good way of thinking of it. All right, so it ranges from 0 to 14. We'll talk about where these numbers come from in a little bit later.
Parents, just a reminder to approve your time before you leave. Connie Sawyers, if you'll come by my office, please.
But it is possible to go below 0, and it is possible to go above 14. But that usually doesn't happen naturally. That would happen because somebody's intentionally making a very concentrated solution. Right in the middle, pH of 7, that is considered neutral. We'll talk about why it's neutral, but that pH of exactly 7 is not considered acidic or basic. All right, so if we go below 7, so anywhere from 0 up to 7 or even below 0, anything on that range of the scale is considered acidic. The H plus concentration is greater than the hydroxide concentration. So there's a greater concentration of H plus, meaning the solution is more acidic than it is basic. So 0 to 7, all the way up to 7. So a solution that has a pH of 6.99999, that's still considered acidic. Okay, pH of above 7, 7 and up is considered basic. And for the same reason it would be considered acidic, the opposite is true for it to be considered basic. Hydroxide concentration is greater than the H plus concentration. These are solutions where there's more hydroxide than there is H plus, so it's considered basic. Now the pH scale is each level represents a factor of 10 change. We'll talk about where this comes from a little bit later. It's a logarithmic scale. Hopefully you don't have to ask me questions about logarithms because I can't really explain them. But I do know it's a factor of 10 logarithmic scale. So that being said, if you have a solution that has a pH of 3 and a solution that has a pH of 6, that 3 levels is a 10 times 10 times 10 or 1,000 times more acidic than the pH of 6. So there's 1,000 times greater concentration of hydrogen plus H plus ions in a solution that has a pH of 3 than there has a solution that has a pH of 6. All right, so that's the pH scale. Well, guess what? If you have a pH scale, you can also have a pOH scale. Yeah. pOH scale indicates the concentration of hydroxide instead of the concentration of H plus. Really what the pOH scale is, it's just looking at the solution from the perspective of hydroxide concentration instead of hydrogen concentration. Other than that, it's really no different. It's just kind of everything is opposite. It's the same mathematical scale, 0 to 14. It just, we're now looking at it in terms of concentration of hydroxide. So, just flip your scale. Anything less than 7 would be considered basic on a pOH scale. Anything greater than 7 would be considered acidic on the pOH scale. And of course, 7 would still be considered neutral. Whether you're looking at a solution's pH or a solution's pOH, it doesn't really matter because every solution has both of those values. And not only does it have both of those values, but they'll be opposite in value. So if you had a solution that had a pH of 1, its pOH value would be 13. Or if you had a solution whose pOH was 14, then the pH would be 0. It's essentially the same scale. It's just what you're looking at in terms of concentration, whether it's hydroxide or H plus. Generally speaking, we usually use pH values more than pOH values, but the mathematical relationship between them is always the same. So if you know one, you know the other, and we'll talk about that a little bit later. Okay, so here's the pH scale, just again 0 to 14. The lower the number, the more acidic. So over here in your solution, you can see there's more H plus ions than there are hydroxide ions. So there's a greater concentration of hydrogen, making it more acidic. There's some common things that are considered acids. I know we talked about in the first video that some acids, there are really dangerous acids, but most things that are considered acidic are relatively harmless. Lemon juice, grapefruit juice, tomato juice. Although if you get grapefruit juice or lemon juice in your eye, that's not going to feel very good. Really what it boils down to, whether an acid is dangerous or not, is not really whether it's an acid, it's just how concentrated it is. That's really the key. 7, pure water right in the middle. And then as we get down to basic, you'll see these big orange blobs. Those are your hydroxide ions, and they are outnumbering your hydrogen ions, so we're becoming more basic. All right, I'm going to wrap this one up here. we'll stop here. We'll pick up at this point on the next one. I don't want these videos to get too terribly long. So there's your quick view at acids and bases and the pH scale. Next time we'll talk more about pH, and we'll look at the calculations that are involved with it. So until next time, see ya.